So let's try and generalize this fast. Let's say we have a function f, okay? But we don't know what it is this time. We don't know it's x squared. We just have no idea. And we want to start here at a and end here at b. We don't know those numbers either. They were 1 and 5 in the previous problem. We already know from what we've just suffered through is that the true area should be the limit as n goes to infinity of the sum k equals 1 to n of this formula. And the formula always had the width of each rectangle, right? So how wide would our rectangles be here? So you need to know how wide this is first, right? Which is b minus a. But then you want to divide that by how many rectangles, which are n. So we're going to have b minus a over n. That's the width of each rectangle, right? That's our width of each rectangle. And then the height of each rectangle will be f times, now, remember how we did this? We started at the left end point. What's our left end point here? A plus, we're going to start jumping, like one jump, 2 jumps, 3 jumps, 4 jumps, right? So that's going to be k times, how big's our jump? B minus a over n. And that right there is the general formula for the true area underneath the curve. As long as you supply me with f, right? If you give me f, I should be able to plug that into f and get an expression. The problem is we needed those formulas for common sums, right? And that requires that the function f is a polynomial. Like we used x squared, right? So if we square this, isn't everything a polynomial in here? Like k is a polynomial. But if this were like sine x, right? If our function was sine x, you are not going to have common formulas. You won't be able to do it. You'll be stuck. So Riemann sums are only good for polynomial functions, all right? But this right here, if you can believe this, all right? If you believe this, does it make sense what everything is in this formula? Width of each rectangle, height of each rectangle at each of the endpoints, add them all up, and get a formula for that, and then at the end, let the number of rectangles go to infinity. Yes? Okay, now, we talked about last class the fundamental theorem of calculus that said, if you want this area, right? If you want the area under a function, all you have to do is put your two numbers here, right? A and B. And then we said just find the antiderivative. And then plug in the two endpoints. Didn't we say that? That was our big result from last class. Okay? It's like if you do this, you don't need Riemann sums. Fundamental theorem of calculus provides us with that. So, do we see now where this notation comes from? Let's see if we can. So do y'all see that this right here is actually, isn't this how wide each rectangle is? That's our change in x, right? That's this. That's dx. That's that little infinitesimal width of each rectangle. Okay? That's what so this right here is the dx in the formula. And then this right here is what? Well, that's just the function evaluated at some value of x, right? So that's your f of x in the formula. And this is not a sum, it's a limit of a sum. And so we have a special notation for the limit of the sum. We use the integral sign. Okay? Do y'all see how that notation means you're going to take a limit of the summation of the height of a rectangle to the width times the width of it? That's what that means. This will become very useful later, because if you can just interpret this as just height times width, when we start taking functions and wrapping around axes and trying to find volumes, if you understand that each piece of this formula is just part of a bigger formula, you'll be good. All right? So let's do the problem we just did using the fundamental theorem of calculus. The problem we just did is we wanted to know the area under x squared between 1 and 5, right? So we just go here, 1, 5, x squared, dx. Antiderivative of x squared is 1/3 x cubed. And then we had this thing called the evaluation bar. We put the 1 here and the 5 here. And then this is last class again. I drew the two parentheses, which allows me to plug in the two endpoints into the antiderivative. So first we plug in 5. So we get 1/3 times, what's 5 cubed? 125. And then minus 1/3 times 1 cubed, which is 1. So what's 100? What's 1/3 of 125 minus 1/3? That's 125 thirds minus 1/3, which is 124 thirds. That's the exact answer we just got that took us like forever, isn't it?
Yes, sir.
We love the fundamental theorem of calculus.
Wait. Yes.
Right? That's the same answer. And it's not a coincidence. Look, there are fundamental theorems in mathematics, all right? Anytime you hear fundamental theorem of, that means it is like a big, huge accomplishment, okay? A human accomplishment. We have a fundamental theorem of algebra. Do y'all know that? There is a fundamental theorem of algebra. Not many algebra classes talk about the fundamental theorem of algebra, but there's a fundamental theorem of calculus, fundamental theorem of algebra, and as you move on, there's fundamental theorems within each kind of core subject. So this one for us is a big one, and you can see why. I mean, it's amazing, I think.
Who was able to discover this?
Well, I mean, this is not only Newton and Leibniz, but I mean Riemann. I mean, it's been over time. Yes.
So that mainly that entire process was to figure out the fundamental theorem.
The entire process of Riemann sums is. Remember, I started class and I said the whole reason I'm going to do Riemann sums is so you understand where the notation comes from. I don't want you to look at this anymore as, oh, we're just finding the antiderivative. I want you to look at this as we're adding up a bunch of rectangles. And how do I know they're a rectangle? It's the function's height times the function times the width of the rectangle. All right? And like I said, it's because of what's coming later. You will not have to do any Riemann sums by hands. There are Cal 2 classes where you are required to do Riemann sum by hands. I'm not a fan of it because then we have this, right? It's like, damn. Okay, so one more thing about, well, not one more. We're going to start into the notes a little more. But I wrote up a little kind of visual illustration today to kind of reconvey just how awesome this is. What the hell? Y'all can't see that, can you? You can't see that this is shaded underneath here, can you?
No.
Okay, I need to fix something real quick. Give me a second. I don't know if I'm going to be able to do this easily. Filling. Style. Copy. Where is it? See if that makes any better. Yeah, you can see that now, right?
Yeah.
Okay, that might be too much. Let's see. How do you spell gray?
Why?
Nope. A-Y. Can y'all see that one? Okay, yes, you can. All right, so what we have here is we have 2x on the left-hand side. All right, it's the function 2x. Okay, and I'm only looking at it between right now, looks like between 3 and 5. All right? What we're saying is that if you want to find the area underneath this function, what you do is you go look at its antiderivative. And what you do is you take the antiderivative and you evaluate the antiderivative at the two endpoints of the interval. So you plug in 3 and 5 over here, 3 and 5, you get the y-coordinate off of this graph and the y-coordinate off of this endpoint and the y-coordinate off of this endpoint, and frickin' amazingly, the difference between these two numbers is the area of that curve.
That is weird.
or the area underneath that curve. That's what the fundamental theorem is saying. Somehow, the y-coordinates of the endpoints here, their difference is the difference of that area. I mean, sorry, not different, is that area. Yeah? Isn't that kind of crazy? That's the fundamental theorem, and that's, yeah, how is that true? Because it is. Here's another example. I got to copy my code again. So here's another one. So here's another curve, right? 3x squared. There's the curve. I'm looking between 2 and 4. If I want to know that area, I actually just go look at its antiderivative, which is x cubed, different function, right? Look at the y-coordinate here, the y-coordinate there, subtract the 2, the area of that's 12, 16 minus 4. That's the theorem. Uh-oh. What did I do?
Imagine being the poor guy who's used Riemann sums for years. And all of a sudden you discovered this.
Well, here's the thing. Riemann sums are very limited. Like I said, Riemann sums can only work with polynomial functions. And you know those common formulas we had? Like I only gave you 3 of them. What if you had like sum k to the 5th power? Like there is a common formula for that, but you'd have to know it. So I think Riemann sums is just really more of an exercise in like what geometrically, what does this all mean? How can we actually ever get to an area? Like, yeah. Okay, look at this one. So this one I think has some pretty profound results. Here's cosine x. Here's the antiderivative, right? So let's take a look at the area. Okay, the area underneath cosine, if we go from 0 to, I'm at pi over 2 right now. What's the area? What's the area, sir? I'm putting you to sleep, so this isn't very interesting to you. So I'll give you the opportunity to tell me what the area under that curve is. The what? Where are you getting 1 from?
Because where it is.
Here?
No, horizontally.
What do y'all think? Does that make sense? All right, why don't you leave? I'm going to ask you to leave. Okay? You can go back and look at the syllabus. If you're sleeping in class or have your eyes closed, okay, not paying attention, you'll leave the class for the day. Okay? Thank you. I have very little patience this week, so I apologize. It's been a long week, and I don't want people sleeping in my class. Very simple. All right, so the answer is 1. Why is it 1?
Because you subtract the y.
Because the difference of these two y-coordinates is 1, right? 1 here, 1 there, right? Okay, but watch what's interesting. Watch what is interesting about this. Okay.
Oh, wow.
What's the area here? Well, okay, according to this, right, what's the answer? What's the difference between these two y-coordinates? 0, right? But you can't have negative area, right? So what's going on here?
Like on the sine x, do you split it in half and then you count it up?
We could, but my question is, the fundamental theorem of calculus is telling us that the area underneath that curve is 0.
Right.
And that means that it's counting stuff above the x-axis as positive and below the x-axis is negative. That's what this means, right? And the question is why? Remember our rectangles, right? Our formula, we said, let's get the area, we do that rectangle. How wide is it? Well, it's the width, dx, whatever it is, right? b minus a over n. But the height is the value of the function, isn't it? So if your point is up here, the corner of your rectangle is up there, then you're going to have a positive number times a positive number. But if you do a rectangle down here, your width's going to be positive, but now your function's value is negative. So when you multiply the two together, you're going to get a negative number. The Riemann sum doesn't know that. Okay, so it's just going to add up a bunch of positive things and negative things, and then at the end it's getting 0. So this is where you have to be a little bit careful, because the theorem gives you kind of like the net area. It counts things above as positive and things below as negative. So what would happen if I continue moving this? I'm going to be negative now, right? Look, I've got more area below than I do above. And you can see that this coordinate, right, this y coordinate is negative, and then that's 0, subtract the 2, and you get a negative answer. So we should get negative area here. And it makes sense because there's more of this than that now. And if I get myself all the way to the end, what happens? You get 0. If I get to 2 pi, right? Because now the amount of stuff up here is equivalent to the amount of stuff here, and so you get 0. Yes, Owen?
In my physics class today,
Uh-huh.
my professor, he says, no matter who you ask as a mathematician, there is such a thing as a negative area.
Mm-hmm.
Do you agree?
Well, we kind of just have that right here, don't we?
Because when I saw that, I was like, okay. that
This is kind of a negative area.
Yes, sir.
Yeah. All right. Yes? Yes.
In this case, so like, if we go back to where we just where the sine function just hit the x-axis on the other side, so we're right in the middle. Okay.
You want to go back to that?
Why, so that area not be 2?
Why would this area not be 2?
Right.
Because,
I'm thinking like maybe you just add them up.
yeah, so how would we fix this, right, to make it 2? We would have to know what this graph looks like,
Yes, sir.
identify its x-intercepts,
Yes, sir.
and wherever it was above the x-axis, we would just go like from 0 to pi over 2, we just calculate the integral. Yeah, okay, so we would basically say, we're going to do this one by doing integral from 0 to pi over 2 of cosine x dx. All right, and that should give me 1 when I'm done. All right, but for this one, what I'm going to do is instead of, I know that it's going to calculate, but it's going to give me the wrong answer. It's going to be negative. So what I'm going to do is the integral from pi over 2 to pi of cosine x dx, but I'm going to just make it negative. And so what will happen is now that negative becomes a positive, and it'll contribute to the sum. So I have to break it up into 2. That's how I would get 2. That's how I get an answer of 2.
Right. Okay.
Make sense?
Yes, sir.
Yes.
You would not try to use absolute value and say add them up to see what.
Yeah, but the problem with the absolute value, what do you mean absolute?
Well, because I know I'm going to get a negative, since I know I'm going to add up to the.
Okay, yeah, you could just say, I just going to take, like, break it up and then just take the absolute value of all your answers. You could say that, yes. I thought you meant, like, do the integral from 0 to pi of the absolute value of cosine x dx. And the problem with that is that the antiderivative of an absolute value is a little more complicated. So, James, let me do this. Let me move the left-hand side like this. Why is that giving me a positive answer?
Maybe it's doing what you told me.
Broke the game.
No, this should be giving me, I should be getting a negative answer here. Where's the positive area? Maybe I did something wrong. I threw this together literally really fast. Something is wrong in my code. All right, the math is right. We should be getting a negative answer here. Not quite sure why we're not, but is the antiderivative cosine sine? Yeah, did I put sine here? Okay, we don't have time to get into why that's wrong. I think you get the general idea, yes?
Yes.
Okay, so some things that we need to establish before we move forward. Okay, we did this last class, right? That was the big idea here.
Yes, sir.
Okay, antiderivative, evaluation bar, just take the difference at the two endpoints. We call that the definite integral. Anytime you have a and b, that's now called the definite integral. You will not have a plus c ever again. whenever you have those numbers on the two endpoints. Okay, so here are some examples. We won't work through these. I want to get to some properties. So look at this first property. If you want to find the area underneath any function, and you want to start at A and end at A, your answer is 0. Does that make sense to you? Because the interval is, there's no width to it, right? So you should have no area. That make sense? Okay? All right, this one right here. If you go from A to B, okay, so let's say A is over here, B is over here, you want to find that area, that's equal to the opposite or negative of going from B to A. So it's like if you reverse the order, if you reverse your order, so let's say here's A and here's B, you want this, you want that area. Okay, whatever that area is, if you reverse it and you go from B to A, you're going to get the same answer, it's just going to be off by a sign. And why is that? Why do you think that would be true, that you would be off by a sign if you reverse the direction? What changes in here? Does your height change? That's right. This width right here is going to be A minus B over N instead of B minus A over N, and so you're going to have a negative width each time. So you'll have negative width each time, and it will be off by a sign. All that you need to know is that if the limits of integration, if these two limits of integration switch places, you get the same answer, just negative or opposite. Okay, what about this one? The area underneath a constant function is just the constant times B minus A. So if we have a constant function, right, flat, let's say that constant function has a value of k, so it's always up here at k. Does it make sense that the area would be k times b minus a? Just this height times that width. So you don't actually need to go through and do any work, but you know, that's only with a constant. Only with a constant function. All right, here's some other properties, and we kind of already know about these properties. If you have a constant in front of a function, the constant can come out of the integral. If our function is greater than 0, that means greater than or equal to 0, that means it's above the x-axis, doesn't it? Then our area should be also positive, or if at worst 0. That's just saying as long as your function's above the x-axis, expect to have a positive answer for area. Yes?
What if we have a discontinuity?
That's a great question. What if you have a discontinuity? You mean within the function when I draw it?
Yes.
Like, let's say we have a function that does this.
Like for example, 1 over x and one of your points is 0.
Okay, so you're asking what if we have a function that has like a vertical asymptote like this? And we want to know the area there? That's the next section. Yep, they're called improper integrals, and that's going to be on your test, so I got to get to it. Okay, but let's get these properties out of the way. Okay, if your function's positive, expect to have a positive answer. If your function's negative, then expect your area to be negative. Now this is a nice one. It says that if you're trying to do an integral that goes from a to b, and c is some number in between, then you are free to split this up into two integrals. One integral that gives you the area from a to c, and then another integral that gives you the area between c and b. So do you see how that works? Go a to b, that's equivalent to going from a to c, then c to b. I know c doesn't make sense being in the middle, but yeah?
Yeah.
Okay. All right.
If you got a little bit of dyslexia, it works just fine.
Why is this not scrolling? I thought I saw a hand go up. Hand go up? No? Okay, if f is an even function, so remember even from college algebra, even meant that you were symmetric over the y-axis. If you have an even function, then if you want to take and find the integral from negative a to a, so let's say we have negative a here to positive a. Notice these are the same numbers, just opposite.
Yes.
Okay, if you want to know that area, right? Then instead of finding the area from negative a to a, you could just find the area from what? 0 to a, just find that answer and then double it. But that only works for even functions. How do you check if a function is even? You have to, you can, without graphing, you have to show that f of x is equal to f of negative x. Plugging in a positive value is the same as plugging a negative in. That's the check for even functions. Okay. What if f is odd?
Then it would be, if you plug in a negative number, it'd give you a positive.
Yeah, so if you have an odd function, then f of negative x is equal to negative f of x. So what's happening on the right, the opposite of it is happening on the left. So what could you tell me about the area if you went from negative a to a?
It'd be negative.
It would be 0. See, look at this right here. This is an odd function because it's a reflection. It's not a reflection over the y-axis. It's a reflection over the origin. It's like a double reflection. Reflect here, reflect there. That's an odd function. So you can see that if I go out here to a and then go this way to negative a, right? Like that. Then those areas will cancel each other out. So you should get 0 there. Right? Because one's above, one's below. Okay. All right, there we go. Now, that was the homework. Someone posted that last time, or did I? I did. Did anyone work through all those yet? Okay, were there any like issues with them? That's basically like going back, like you should find that when you do those problems, like, you know, it's integration that is, I think it's mostly straightforward integration. Okay, so all we're doing is applying the fundamental theorem now. All right, that leads us to the last section that will be on the test. And that's 6.6, which is called improper integrals. All right, so improper integrals. There are two types of improper integrals that we're going to deal with. And I'm going to show you those first, and then we'll go through them. The first type, okay, type 1. And then we'll do type 2. Okay, type 1 is not the one that, Rifa, I'm saying that right. Rifa asked about discontinuities. And that is actually what we call type 2 improper integral. So let's start with that since it was brought up. What if we had the function like f of x equals 1 over, let's just do x minus 1. And let's say we wanted to find the area under that on the interval 0 to 5. What's the problem that we would run into? We have a problem at 1, don't we? This function is undefined at 1. So if you were to sketch this function, at 1, you would have some sort of vertical asymptote like this. And let's see, at 0, where would we be here? 0, we'd be at negative 1. And then this is at 1, right? So we would have, it would be doing something like this. It would be diving down like this. Then on this side, it would be going up like that, and then going like that, and they would stop here at 5. You know, it'd be somewhere. So what we're trying to do is find the area, and so we're talking about the area here and the area here. And do y'all see why that's problematic? Because this little region just like keeps going, gets thinner and thinner, and this region here gets thinner and thinner. So it looks like maybe the answer might be 0. Like maybe this area cancels that one. I don't know. But That's type 2. We're not ready for that yet. We'll do type 2 next class. We're going to at least start looking at what's called type 1. And type 1 goes like this. Instead of taking a function and starting at A and then drawing the function and stopping at B, I want us to go forever. So imagine a function that like asymptotically approaches like the x-axis. All right, so we have to have some sort of asymptote for this to work. Imagine that that gets closer and closer to the x-axis, gets smaller and smaller as we get closer. Can we talk about the area underneath that curve if we allow it to go forever? Make sense? So instead of going from A to B, we're going from A to what? Infinity. Okay, so that's type 1. Type 2 is where you have a problem, a discontinuity within the interval. Type 1 is where we're going to let our interval get really large. See the major difference between those two? And there are problems where you actually have both of them happening at the same time. Okay, but we'll deal with that at the end. Okay, so the notes for improper type 1, we call type 1 infinite intervals. Infinite intervals. Does it make sense, that wording? Your interval, instead of it going from A to B, your interval is infinite. So our integrals will look like this now. Our integrals are either going to go from A to infinity, right? So that would mean like, I think I have pictures. Here's an example of a function, of an integral where you go from A to infinity. So the left endpoint, you have a nice defined endpoint, but to the right, you never stop. Okay? And then you could have it the other way around, where going out this way, you never stop, but you stop on the right. And that would look like this, negative infinity to B. So instead of A to B, it's negative infinity up to B, right? And then you have the possibility of going out both directions. And that would be something like this, going from negative infinity to infinity. That means you go out that way, you never stop. You go out this way, you never stop. So we try and find the area underneath that. Now, do y'all understand, like visually, what these infinite intervals look like? Yes?
Would technically the area underneath that be infinity?
Well, we don't know yet. Okay, sometimes yes, it's infinite. Sometimes no, it's not. Okay? It's all going to depend on the function itself. So going back up. Okay, we're going to face one of these three types. Okay, it's going to be one of these three types. Notice that the limits of integration are infinite. You've got infinities in here, right? So they're infinite intervals. So provided that these limits exist and are finite, we have the following definitions. If you ever see this integral, A to B, what we're going to do is we're going to transform it into a limit. And let's just take a look at what this limit is. If we ignore the limit for right now, isn't that basically like the fundamental theorem of calculus? It's instead of using B, we're using T, right? So what you would do is you would treat that like you did the previous problems. You would find the antiderivative, you'd plug in what? Plug in T, then you'd plug in A, you'd subtract, right? And you get an answer. And then what you do is you let T go to infinity. So it's kind of like you're saying, all right, look, I'm going to find the area under this interval from A to T, find an answer, and then let T go out forever. Does that make sense?
Yeah,
Let it go to infinity. So it's kind of like, take this picture, and we find the area from A to T. We find a formula for that area, and then we let T take off. Okay? And see how it changes the formula. Now, if we want to do it the other, I thought I saw a hand. If we want to do it the other way, this one, we do the same exact process. We convert it to a limit, but this time what changes?
It goes to negative.
Yeah, it's going to be T to B now, but T is going to head off to negative infinity. So we find a formula from going from T to B, and then we let T take off that way. So what do you think we would need to do if we had infinity, negative infinity on the bottom and positive on top? So we would actually have to break it into two. if we want to go from negative infinity to infinity, what we'll do is we'll go from negative infinity to any point we want, a, and then another integral that goes from a to infinity. So we'll just split it into two. Now each of these are their own limits. Now we've already learned that with limits, it is possible for a limit to not exist, right? So back up here it says, if these limits exist, if the limits exist, we say the integral is convergent. As long as the limit exists, the integral is called convergent. If the limit does not exist, then we will say the integral is divergent. Convergent means you're going to get a limit that's going to give you an answer, and divergence means you get something other than a number. All right? You could get infinity, but you could also get something that just the limit doesn't exist. So I think we have enough time to maybe just do one. So let's do that one. So that is the function 1 over x squared, and we're going to go from 1 to infinity. So when we write this, the first thing what we'll want to do is we'll want to make sure we understand that we're dealing with the type 1, right? Yes. We're dealing with type 1. Type 1 means we have an infinite interval. And because it's an infinite interval, we want to convert this to a limit, right? Now, we also should pay attention to our interval because of the problems that are coming later. If I draw this, here's 1, right? That's where we're starting. And we're going this direction forever, yes? Yes. Okay, just check with the function. Does the function have any problems on that interval? No, right? The only place that function has a problem is at 0. And 0 is not in there, right? Okay, we want to check, because if it is, then we have the type 2 is happening at the same time. So we only have type 1 here. So what we'll do is we'll say, okay, this is equal to the limit. I'm going to let t take off to infinity. And remember, t is the right endpoint, yes? Yes. So I'm going to go integral from 1 to t, right? So that's the one that's taking off, going that direction. And what am I integrating? 1 over x squared dx. Okay, so now ignore the limit and just do the fundamental theorem of calculus on this. So just go find the antiderivative of that. So keep the limit here. We're not going to do the limit yet. The antiderivative of this is negative 1 over x. That's the antiderivative, right? But then we need the evaluation bar, and we need down here 1 and up here t. Okay. Still not going to do the limit yet. I'm going to write the limit down again. T is going to go to infinity. And now I'm going to do a bracket here because I'm about to do 2 sets of parentheses. This is what I've been doing every time I've been using the fundamental theorem of calculus, right? I find the antiderivative, I put the evaluation bar, then I plug in t first, then 1, right? So t goes in for what? For x, right? So what does it become? Negative 1 over t, okay. And then I plug in 1, what do I get? Negative 1 over 1, which is just negative 1. Okay, now at this point, let t go to infinity. So what happens if t goes to infinity here? That goes to 0, right? And this has not impacted by t at all, right? So this goes to 0, and that's just negative 1. That's just 1. So guess what? We have a convergent integral. The area under that curve from 1 to infinity is 1. It's finite. So even though we're going out forever, right, 1 over x squared, it dives down like this. That area, if you could go forever, is finite. What does that mean?
Yeah, how do you get, I mean, how does that actually, like, I guess it's just not wrapping around the whole, you have an infinite, goes off forever, I mean, ever.
Yeah.
You get 1.
Yeah.
It's like, you know, heads out of the galaxy, the answer is 47.
Yeah. Well, I might be able to convince you of this.
Okay.
Maybe. I might. So take a look at this idea. We can't, that's it. We can't go any further with any more examples. But the question is, how can you have that go forever and be 1? Maybe this will be a good argument. One of my favorite arguments. is just look at the repeating decimal 0.999 forever. Okay? That is actually the number 1.
Right.
Okay? Now, the reason why it's the number 1 is if we call this x, then if I multiply it by 10, what do I get? So what happens to anything when you multiply it by 10 with the decimal? Moves over. So this is just 9.999 forever, right? Okay, what if I ask you what's 10x take away x? Just algebraically, what's 10x take away x? 9x. Okay, so do y'all agree that's 9x? But that has to equal this minus this, right? And what's this take away this? Well, this is 9.9999. This is 0.999. So just the 0.99s go away, and you have what? 9, right? So we have that algebraically 10x take away x is 9x, but in this particular case, it's 9. And so x has to be 1, right? So we're saying this is 1. Now, let's look at this decimal written out. What's this first 0.9 mean? That means 9/10 plus 9/100 plus 9/1000, right? And that goes forever, doesn't it?
Yes.
So this is not 1, right? But you add a little bit more, and that's getting you closer to 1, right? And that's closer to 1, and that goes on forever and ever, but I'm telling you at the end it is 1. So I'm trying to convince you that the idea of having something add up forever and be a finite number is something that we can see from even this. I don't know. We'll have more time to talk about this when we get to series, but this should be somewhat counterintuitive. You have an area that goes forever, so there's got to be something there, right? And it keeps going forever, so how can that be finite? It's counterintuitive, but it's the way it is. The whole thing is 1 over x squared is just dying fast. It's converging down to 0 fast. If you try it for 1 over x, then what's the antiderivative of that? Natural log, right? And then what you're going to wind up doing is, I'm kind of going shorthand here, but you'll have t here and 1 here, and you'll go there, and you're going to let t go to infinity. And when t goes in here and you let it go to infinity, you get infinity. Natural log of infinity is infinity. And so what we wind up determining is that this one diverges. And it's because it drops down to 0, but just not fast enough. But 1 over x squared drops fast enough. And so every function you have to look at and evaluate.
So
Yes?
it's kind of like you're approaching a finite area or a finite boundary, but you're pretty much never actually getting there. Like you're infinitely getting there.
So one way you could look at it is this. If you take 1 over x squared dx, right? And we go from 1 to, let's say, that number right there. That's a definite integral. A and B are numbers, aren't they? You could go ahead and do the fundamental theorem of calculus here, and what I can tell you is your number is going to be really, 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 really close to 1. Okay?
So it's technically not 1,
Well,
but it's close enough.
no. This is close to 1. Okay? This is close to 1, but that's closer, right? And if you can wrap your head around the idea of going to infinity, it is 1. This is a big deal because, I mean, like, if you ever stop, you're not 1. But I'm telling you, we're not stopping. Ever. Which means that if that was possible to go forever, that is what 1 would be.
Okay, I'm having a really hard time.
You should have a hard time with that. Yes, this is different. This is a different sort of thinking. All right? We'll have more time to think about it. So I gave some students, I know it's time to go, but I gave some students some problems to look at. And this was just, I don't normally do this. This was my exam 2 from last fall. And that's the problem. Some students came by and wanted to look at some problems that, to practice. And so I gave them these problems. So this was my 6th question. The only reason I'm telling you is because I've already shared this with some students, and I don't think it's fair to not share it with everyone. So these are problems. This was the exam, all right? Don't ask me for the solutions. okay? Don't ask me, and don't expect this to be your exam, all right? But this gives you some flavor of what I asked. That first one is hopefully obviously a trig sub. The second one is partial fractions. The third one is another partial fractions with long division first, and it's a definite integral, so they had to at the end plug in the two endpoints. The third one, right? That's a type 1. We haven't really done one of those yet, and this integration would require what? By parts. That's an integration by parts right there. And then this one right here, this one looks kind of unassuming. Like a basic U sub, but it's a type 2 because it's undefined at 1 and 1 is inside here. So this is a type 2 improper integral. And then this one right here is a type 1, but it's partial fractions. Now all of these problems were taken from the book in some form. Okay, so these aren't just like crazy problems. These are book problems. That gives you some flavor. I looked at this the other day. I was like, why didn't I give more trig sub? Like, it seems to me like I should have put more trig sub in here. But I also don't remember what my fall exam 1 looked like. So, yeah, you know, take it for what it is, but don't sit there and be like, hey, you know, study and, you know, you have a week, but all right, have a good weekend.
Will these examples be part of the video that you upload to YouTube?
What examples?
These right here, will these show up on the video that you upload to YouTube?
It should, yeah, but if you want to, you know, take a picture of it, you can. I'm going to turn this off. What's that? Take them all. I don't care which ones you have.
Real quick.
Yeah, let me turn off my camera.